Hello students, how are you? Welcome back. Today we'll be talking about mutual inductance. Before going towards mutual inductance, we'll very fast recall what was self-inductance. Suppose there is a coil. If current I is going through it, if I vary I or if I is continuously varying, then there will be some amount of magnetic field. Even if I is not varying, there will be a magnetic field over here, due to which there will be magnetic flux over here. Now, if I change the value of I, the magnetic field inside the coil will increase or decrease. That means it will change. If magnetic field will change, the flux will also change. And if there is any change in flux, then there will be induced EMF inside it. And due to that induced EMF, there will be induced current inside it. Okay. So now to know the direction also, what we'll do? Suppose if current is increasing, if current is continuously increasing, if current increases, once again the magnetic field will increase, and due to that magnetic flux will increase, and due to that there will be induced EMF according to Faraday's law. Now what is the direction of current? What does the Lenz's law say? Lenz's law says that induced current or induced EMF always try to oppose the cause which produces it. So here what is the cause? Increase in current is producing the induced current. Increase in current is producing the induced current. So what it will try to do? It will try to decrease the external current. So how can it decrease? If the current is in opposite direction. If the current is in opposite direction. Okay. If it is in opposite direction, then it can decrease. Now suppose if I is continuously decreasing. If I is decreasing, what will happen? Then also magnetic field will change, magnetic flux will change, and due to that the current will also magnetic flux will also change. Sorry. So due to that there will be induced EMF once again. Now this time also there will be induced current. Now what will be the direction of the induced current? Here the current is decreasing and that is causing it. So what it will do? Induced current will try to increase this external current. To increase this external current, it will try to support it, or it will be in the direction of the external current only, so that it can get support. So this will support it. Okay. So I hope self-inductance is very clear to you. Whenever there is any flux linked with the coil, and if it changes, there will be induced EMF inside it. And here the inductance is in the same coil in which the current is varying. That's why it is known as self-inductance. Okay. So now what we'll do? We'll move towards mutual inductance. Mutual means for any two person or any three person. Mutual means not single. Self was myself or me. It is for self, and mutual means with someone. Okay. Suppose I have a coil attached to a battery. Okay. I take another coil which has a galvanometer with it. Okay. Now if I pass the current through this, what will happen? There will be magnetic field over here. Magnetic field will be generated, and due to that there will be magnetic flux. Okay. Now if I vary this, the magnetic flux inside this also changes. Okay. So first of all we will draw the magnetic flux. Magnetic flux is not like a single line. It can go up to infinity. Suppose if magnetic flux sign is like this. Okay. This time. So what will happen? The magnetic flux due to this coil is also linked with the magnetic flux with this coil also. The magnetic flux that is linked in this coil is also linked with the coil 2. Suppose let us say this is coil 1 and coil 2. So if I vary this current, let us say current I1 that is in the coil 1. If I vary this current, if I increase or decrease this current, the number of magnetic field lines over here will change. If the magnetic field lines over here will change, then the magnetic field lines over here will also change, which means that the magnetic field or the magnetic flux is changing over here is depending on the current that is varying in coil 1. The magnetic field lines in coil 2 depends on the variation of current in coil 1. Okay. Here there is no current, so there will be no current passing. But due to this flux linked with it, if the flux linked with it changes, then there will be induced EMF or induced current produced. So can I write that suppose the flux in one round is for phi 2 is equals to flux, I can write it as phi 2. Okay, then the total flux in coil 2 will be equal to n into phi n phi 2. N is the number of turns, or I can also write n2 because here also will be having n. Okay, now this depends on the current of coil 1. The flux in this depends on the current of coil 1. Okay, so can I write is equals, or it is proportional to I1. Phi T2 is proportional to I1, that is flux in this coil is directly proportional to variation in this current. Okay, so phi T2 can be written as M I1, where M is nothing but coefficient of mutual inductance. Coefficient of mutual inductance, or I will directly write mutual inductance. Okay, so if I want to write M, I can write M equals to phi T2 upon I1. Phi T2 upon I1. Or if I remove this T, I can also write it as phi N phi 2 upon I1. Okay, this will be the condition for magnetic mutual induction or mutual inductance. Now suppose if we want to find the mutual EMF, okay, or induced EMF. So induced EMF will be in the coil 2, so I will write E2. E2 will be equals to minus of change in flux into total flux upon dt according to Faraday's law. So what is the change in flux? Here we know what it is, Mi minus d Mi1 upon dt. Okay, what is I1? Oh, sorry, M is constant, mutual inductance is a constant term, so I can remove it outside, is equals to di1 upon dt. Here there will be minus sign as over here, but if I put this E in modulus, then this will also become E mod. Means negative sign only gives the direction. Okay, so from here once again I can define the mutual inductance. Once again I can define the mutual inductance. What is mutual inductance? If current passing through it, the rate of current changing is 1 ampere per second. If this term is 1, okay, if this is 1, I'll write it over here once again. E2 equals to M and di1 by dt is equals to 1 ampere per second. So then I can define this mutual inductance as the induced EMF in coil 2 when the variation in current in coil 1 is 1 ampere per second. Okay, once again, the mutual inductance is equals to the EMF in coil 2 when the change in current in coil 1 is 1 ampere per second. Okay, if you want to find the unit, we can find the unit from over here. SI unit, what will be SI unit? Phi is Weber, unit of phi is Weber, that is flux, Weber upon ampere, or you can also say Henry. That is same as it was in mutual self inductance. Okay, I hope this much is very clear to you. What is mutual inductance? Mutual inductance is the EMF that is linked or induced in coil 2 where there is no current passing. This induced EMF is due to variation of current in this coil. Variation of current in coil 1 produces some induced EMF in coil 2 or induced current in coil 2. That is known as mutual inductance. Okay, self it was 1 only, in mutual it is 2. It is happening in between the 2. Okay, I hope this much is very clear to you. Just copy it very fast. Okay, you can pause the video and copy it. Okay, now we'll find mutual inductance for two coils that are coaxial. Two coils that are coaxial. What does coaxial means? The axes of both the coils are same. Axes of both the coils are same. So suppose we have a bigger coil and in the center of that we have a smaller coil. Okay, there are two coils, one is bigger coil and one is smaller coil. The axes of both the coils are same. Suppose this is the bigger coil and in the center of that a small coil is also moving. Okay, so we need to find mutual inductance due to these two coils. Suppose let us name this outer one is coil 1, which has length will be equal. Okay, or if still you want to write, you can write L1, but length will be equal. Let us say R1 and N1. What is N1? N1 is number of turns per unit length, or you can also write it as N1 is equals to N1 upon L. N1 upon L, that is N1 is number of turns in the bigger coil, or you can say outer coil, coil number 1, and L is the length. For this second coil, let us say name it coil C2. Length will be same for both the coils. Okay, length will be same for both the coils. Radius, let the radius be R2. Let number of turns per unit length be N2. You can also write it as N2 upon L. You can write it in both the forms. Okay. So suppose there is a magnetic field moving in the outside coil. Okay. Suppose we assume that there is a current passing only in the outside coil. There is no current passing in the inner coil. Only the current is passing in the outer coil. Okay. So due to that, there will be magnetic field in that. There will be magnetic field in this outer coil. What it will be? Mu 0 N1 I1. Okay. Can I write it in this form? Mu 0 N1 I1. Okay. So now next what we'll do? We'll find the mutual inductance in between them. So flux linked with that will be equal to phi is equals to B into A. Okay. Flux is equals to B into A. For 1. Flux for phi 1 will be equal to B1 into A. Will be equal to mu 0 N1 I1 A1. Okay. Mu 0 N1 I1 A1. Now what is the magnetic field in B2? That will magnetic field in the second coil. What is the magnetic field? Magnetic field will be equal only. The magnetic field that is in the one will be the same in the magnetic field that is in the second coil, because both are coaxial. जितनी magnetic field बाहर की coil से जाएगी उतनी magnetic field will move from the inner coil also. So I can directly write that magnetic field is the same, that is mu 0 N1 I1. Okay. I hope this is very clear to you. Now the flux in second coil will be, flux in the second coil will be equals to once again B2 A2. Okay. What is B2? It is same mu 0 N2, sorry, mu 0 N1, mu 0 N1 I1 into A2. Okay. Now if this is the flux in singleton, if this is the flux in singleton, then what will be the total flux in total turns? That is phi T2 will be equal to, if there are N2 turns, then it will be equal to N2 into L. Okay. Or directly first time I will write N2 only. Number of flux in N2 number of turns. In N2 number of turns, I will multiply it with N2. And N2 from here I can write N2 is equals to L into N2. Okay. That is L into N2. Can I write it in this form? Okay. So I'll write it once again over here. Mu 0 N1 N2 L A2. Okay. Can I write it in this form? Okay. So now what is the value of this? We have already found out that phi 2 is equals to M I1. Phi 2 is equals to M I1. So I'll put the value of this over here. I can write M into I1. Okay. So I1 and I1. Okay. I forgot to write the I1. M1 and I1 from both the sides will get cancelled. So the total inductance, total mutual inductance in coil 2 will be equal to mu 0 N1 N2 L A2. Okay. The mutual inductance in coil 2 will be equal to this. Okay. If you want to write down the area, you can write down pi r square also, because it is in circular form. But right now we are just keeping it area as A only. Okay. So I hope the concept of mutual inductance is very clear to you. Once again, very fast I will tell you what is mutual inductance. If there is current passing in any one coil, there will be magnetic flux produced in that particular coil also. And the magnetic field line, if there is any other coil near to it, then the same magnetic field will also produce flux that are linked with the second coil also. So if the flux is linked with the second coil, and if the current in the first coil changes, then the magnetic flux in the second coil will also change. And if the flux changes, we know that according to Faraday's law, there will be induced EMF. This induced EMF is due to mutual inductance. This EMF is due to mutual inductance. That is, because of me, you are getting something, that is some mutual inductance between two, or mutual understanding between two. Okay. I hope this topic is very clear to you. So students, keep studying. Thank you. Have a nice day. All the best.